Correlation and regression. In this video, we're going to be looking at how to calculate the correlation coefficient and interpret the regression line equation. So we have a table here showing the lengths of the Dubrex glands in millimeters for 6 people of different ages. Note that when we have two sets of data and we're comparing them, X is the explanatory variable and Y is the response variable. Response because that's what we are actually measuring. So these people may have come in to see their doctor, for example. Their age was a given, but then their Dubrex gland was measured. Here's the data in a graph, and as we can see at first glance, it looks like we've got positive correlation. Okay, and back in year 8 or whenever, that's just what you would have written down, positive correlation. But now we've got a way of quantifying it. So as it says, we can use the calculator to quantify the correlation coefficient, which has the letter R. We can also work out the equation of the line of best fit, although that is not an expectation, even though the information comes up at the same time as the correlation coefficient. So the equation is y equals a plus bx, and your calculator would give you the values of a and b, where a is the y-intercept and b is the gradient. So to work them out, you would use menu 6 and then press button 2, which represents y equals a plus bx. You type in the values for x and y as shown above, remembering, of course, that x is your a and d is your y. You press equals after each one, then you press the option button and number 4 for the regression calculation. Here's a pretty blurry picture of what I got on my calculator. So as I say, a is the y-intercept and b is the gradient. The information we really want to extract from here for our purposes is the correlation coefficient, which is 0.991 to 3 decimal places. So some information about correlation coefficients. They are always between -1 and 1. I've used the modular signs there to show that the size, the magnitude of the correlation coefficient is always less than or equal to 1. If R is greater than 0, then as you'd expect, that's positive linear correlation. If it's less than 0, that's negative linear correlation. The closer to 1 or -1 you're getting, the stronger the linear correlation, and we will, determine whether or not things are valid in terms of correlation or not when we get to hypothesis testing. So just remembering, as I say, back in year 8 we were looking at positive correlation, negative correlation, no correlation, and sometimes you'd have to decide whether or not you were going to draw a line of best fit or whether it's worth it or not. A line of best fit is only appropriate if you have strong or reasonably strong linear correlation. Okay, it doesn't matter whether it's positive or negative, as long as it is strong. And as we're saying, that's how close it is to 1 or to -1. One expectation is that we can put the data into context. Whether we've got a correlation coefficient or a regression line, we can talk about it. So number 1, if R is positive, then as X goes up, then Y goes up. And if R is negative, then as X goes up, Y goes down. And as I say, we're putting these things into context. Okay, so for example, with our Dubrex gland, where we had positive correlation, then we'd be saying that the older someone is, the longer their Dubrex gland. But if it was negative correlation, we'd be saying the older they are, the shorter their Dubrex gland. Number 2, the y-intercept A is the value of y when x is 0. So whatever x represents, if there was none of it, then the value of y would be the value you get then. Number 3, the gradient B is the value that y increases or decreases by when x increases by 1. So we'll be looking at that, but that'll basically be for every extra year of age, we would expect the Dubrex gland to be lengthened by a certain amount. Number 4, interpolation is good and extrapolation is bad. So interpolation is when we're looking at values within our data range. Extrapolation is when we're looking at them outside of the data range, which has to come with a health warning. And then number 5, you can use X to estimate Y, but you can't use Y to estimate X. We'll see an example of that in a minute. So we're just going to finish off with a few questions related to this. So we can see at the top left, the values of A and B have been put into the equation. So D, the length of the Dubrex gland, is equal to 7.32 plus 0.39 A, where A was the age, and we've got our correlation coefficient of 0.991. So first question, describe the relationship between the length of the Dubrex gland and age. So referring back to the previous slide, because it's strong positive correlation, we can say that as a person gets older, their Dubrak's gland is going to be longer, because as x goes up, so does y. Is it appropriate to find an equation for the regression line? Well, we've got one, okay, but it wouldn't be appropriate if our correlation wasn't strong or reasonably strong. And r equals 0.991 is a very, very strong positive correlation. So yes, it is appropriate to find an equation for the regression line. So it's quite possible for them to give you a regression line equation for correlation which isn't strong or reasonably strong, and then ask you to work out something. But then they'd normally follow it up by saying, how valid is your answer? And you would say, well, it's not valid because the correlation wasn't strong in the first place. Okay, but you'd still have to actually work out the value and then comment on it afterwards. Anyway, we've got 3 questions here. Find, where appropriate, the length of the Dubrak's gland of a person aged 13. So in this instance, we're only going to find things if they're appropriate to find out. So with this one, a person aged 13, if we look at our age data, the youngest person was 6, the oldest person was 46. So here we are interpolating because 13 is between 6 and 46, which means we can use our regression line equation appropriately. And as a result of that, when we substitute 13 in there, 7.32 plus 0.39 times 13 is 12.39 millimeters. So that would be our answer if we wanted to give it that accurately. Secondly, the length of the Dubrak's gland of a person aged 50. Well, I've just said that the oldest person was 46 and therefore 50 years old. That would be extrapolation because we're now going outside of our data range. Okay, so although we could work it out, okay, I'm not going to because it says find where appropriate, and it would not be appropriate to do that. And then finally, the age of a person with a Dubrak's gland of length 20 millimeters. Now looking at the Dubrak's gland information, 20 millimeters is within the range. The lowest is 10, the biggest is 25. However, plotting data into context 0.5 says you can use x to estimate y, but you can't use y to estimate x. So given that a is x and d is y, it's okay to use a value like an age of 13 to find the length of a Dubrak's gland, because that's turning x into y to estimate y, but we're not supposed to do it the other way around. We're not supposed to use Dubrak's gland information to work out ages. So again, that final one is not appropriate, and I will not be doing it. And then finally, we've been asked to interpret the values of 7.32 and 0.39 in our regression line. So looking at point 2, putting data into context, the y-intercept a, so in this case 7.32, is the value of y when x is 0, i.e. when a is 0. So that is implying that when you are born, i.e. x is 0, you are 0 years old, that your Dubrak's gland is 7.32 millimeters long. And then the value of 0.39 in the regression line, that is the gradient. The gradient b is the value y increases by, in this case it is going up, when x increases by 1. So for every extra year of age, the Dubrak's gland is 0.39 millimeters longer. And that concludes our correlation and regression introduction.